Okay, so good morning. This is a review of the force, net force, on a current loop in a constant magnetic field. So let's say that we have a constant magnetic field and we have a loop of current which is in a loop of wire which is in a rectangular shape. And that rectangular shape has a width of W and a height of H. We've looked at this problem before. So this is just a review. And I want to know what is the net force and net torque on this loop of wire. So in order to find the net force and the net torque, we are going to look at the force on a current carrying wire, the magnetic force on a current carrying wire, F equals IL cross B, and actually it is the most general form is DF is equal to I DL cross B, and then you can integrate that in any varying field or current or space. And so the formula that we can use here is the one for constant current in a constant magnetic field. So it's a special case of the integral. And so then we can look at each side separately. We can look at the top side, the right side, the bottom side, and the left side. And we can see that the cross product, which will give us the magnitude of the force of the magnetic force on any given side, is going to be ILB sine theta, and the direction is going to be given by the right-hand rule. RHR stands for right-hand rule, where we take our fingers in the direction of L, cross them towards B, and the thumb points towards the force. So for each of the current segments, top, right, bottom, left, the current is the length or the direction of the current is perpendicular to the magnetic field, 90 degrees. So for each of these, the 90 degrees, the sine of 90 degrees is 1. So the magnitude of the force on each side is ILB. And by the right-hand rule, we then can find that the force, that each of these magnetic forces points in the direction as shown by taking your fingers in the direction of I, curling them towards B, and your thumb points towards the force. So each side has a force of a magnitude ILB in the direction as shown. So that's a review. And what I want to point out is that gives us, because each force is a magnitude ILB, and each force, the one to the right has an equal one to the left, the one to the top has an equal one to the bottom, so therefore the net force must be equal to 0. So there is no net force. In other words, the center of mass doesn't move. But remember that if you have no net force, you can still have a net torque. So no net force doesn't necessarily mean it won't rotate. You can still rotate something with no net force. But in this case, jumping ahead, because these forces, if you think qualitatively, clearly do not rotate the loop, there is no net torque either. What these forces do is they all tend to pull the loop towards the outside, and it would make, if the loop were allowed, it would change the shape of the loop and make it circular. But in any case, but let's just think more about the torques, because the torques is where we want to go with the next problem. So remember the definition of torque. The definition of torque, I have a few things written down here. The definition of torque given by any force is R cross F. The torque is some radius vector. We have to choose. Remember, what we have to do is choose an axis of rotation. And so then the radius is how far from the axis of rotation the force is being applied. And then we have to cross that with the force, R cross F, or RF sine theta. And so the net torque is the sum of all the individual torques. So we've got the net torque here is going to be the torque due to the force on the right, the torque due to the force on the top, torque due to the force on the left, torque due to the force on the bottom. Now, what axis of rotation will we use? Well, because it's not rotating, it actually doesn't matter, right? This is an equilibrium problem. But let's just say, for example, I take the axis of rotation through the center, going up and down, right? So that means that, for example, the radius vector, the radius vector for the force on the right is there, the radius vector for the force on the left is there, and there is no radius vector to the force on the bottom and the top. Well, actually, I mean, all right, but where I drew them there's a radius vector, but because, wait a second, sorry. Actually, I gotta be a little bit careful because of where I drew the forces. Because the force is the same anywhere along the top. The net force on the top is actually through the top center. So the force on the top, for example, that force there should be through the center of the side, and the force on the bottom should be through the center. Each of these forces should be through the center, and the axis I chose was through the center of the loop. So those forces should be parallel, or should not only be parallel to the axis, but should be along the axis, and that means the radius vector has a radius of 0. So R would equal 0 for those two forces. In this case, R would equal W over 2, right? And in this case, R is equal to W over 2, since this whole length here is W. But for the torque on the top, R is equal to 0. For the torque on the bottom, R is equal to 0, because there is no distance, not the way I drew it, but correctly, there is no distance from an axis through the center, and those two forces. On the right and the left, the radius vector is W over 2, but the reason why the torque, let's just go around the circle. The torque on the top is 0, because R is equal to 0, so that's torque on the top is 0 because R is equal to 0. The torque on the bottom is 0 because R is equal to 0. The torque on the right is 0, not because R equals 0, but because the angle between R and F is 0. Remember, the cross product is RF sine theta, so that's 0. And that was the left. The left and the right are the same. That in both cases, theta is equal to 0, theta is equal to 0, R is equal to 0, R is equal to 0. That's why each of the torques is 0. I do want to point out, just as a reminder about torque, net torque is the sum of all the individual torques. It's not R cross F net. Because again, if it was R cross F net, then if F net was 0, torque would always be 0. But you can have rotation without translation, meaning if F net is 0, torque net could still be non-zero. And we'll see an example of that soon. Okay, so this is what I just said. You can have a net torque without a net force. Okay. You might ask, what if I chose a different axis? Let's just say I just chose an arbitrary axis like here, then this R would be shorter, this R would be longer, but the angle between the R vector and the F vector on the right and left would still be 0, and this R and this R would be the same. And therefore, the one on top would give a net torque. The one on top would give a torque. That torque would tend to rotate the thing clockwise, and the one on the bottom would give a torque, and that would rotate the thing counterclockwise, the loop, with a net effect of 0. So the net torque is still 0 regardless. You can choose any axis you want here, and you will find that the net torque is 0 for this loop in this field, no matter what axis you choose. Okay. Therefore, so that's just a repeat of that. Okay. So that was a review, but a little bit more detail to try to let you remember about some things about net force and net torque and how to calculate torques. So now let's just choose a different situation. I'm going to again have a current loop. And by the way, let me just jump ahead and say the reason why we're dealing with current loops is because current loops are standard things in physics. Just changed my sound system. Hopefully I sound a little better. In any case, current loops are standard in many ways. They're standard in engineering. They're what are used in motors and generators, current loops. They're standard for electromagnets. Electromagnets are loops of current which are piled up to make a coil. And they're also standard in subatomic physics because a current loop is the equivalent of a single electron going around an atom, and what's called a moment or a magnetic moment. That can be modeled by a current loop. So current loops are actually really, really important parts of physics. So this isn't just a little side thing. This is actually a standard that we're going to use to do all kinds of different, that you can use to do all kinds of different things. Current loops are standard in physics. So you should understand some of this. Okay, so let's take a current loop in a different magnetic field. So the one before was the magnetic field into the board. Here we'll do magnetic field to the right or into the screen. Here we'll do a magnetic field to the right. So remember, I just wrote down, we can talk about the force on each side of the current loop. My current loop is purple, my magnetic field is red. The magnetic force is IL cross B. And again, IL cross B is ILB sine theta, directions given by right-hand rule. Okay, so let's look at each side. Let's look at the top side. The top one, right, the top, that piece of current, remember, and this does have a width W and a height H, that piece of current, I times W times B times sine theta. I is the current, W is the length, B is the magnetic field that it's in, and sine theta, theta is the angle between I and B. In this case, for the top, since the angle between I and B is 0, therefore F on the top is equal to 0. We can therefore make the same argument on the bottom. Actually, in this case, being careful, theta is 180 degrees between the current and the magnetic field. Therefore, still, the F on the bottom is equal to 0. These are vectors. Because sine of 180 is equal to sine 0 is equal to 0. On the right, we again have the F is equal to magnitude I, and there this has a height H, IHB. I didn't do that earlier, I just said ILB, but actually the height and width I could have put in for the other loop, but I didn't. Okay, so this has a IHB sine theta. The angle here is 90 degrees, right? So the angle between the current and the magnetic field, so it's IHB sine 90, which is 1, and that's the magnitude. But what about the direction? What's the direction of the force on this one? Put your fingers in the direction of I, rotate them towards B, and now your thumb points out of the board, so this is going to be out of the screen. So the force is going to be out of the screen. It's going to push it towards you. By the same token, the one on the left is going to have a force F left is equal to, it's the current through that part is I, the length of that is H, the magnitude of the magnetic field is B, the angle is still 90 degrees, this is 90 degrees between those two, I, the length and the B, so it's sine of 90 is 1, and the direction, put your fingers pointing upwards, rotate them towards the right, and that means your thumb points into the page, so that is into the page. So now, H, I had already written this on a new page. There you go. So, H, this is H, not L. Because remember, again, the loop has a height H and a width W. Okay, so the magnitude of the force on the right is IHB, on the left is IHB, but now they're pointing in and out of the page. What is the net force? What is the net force? Okay, think about it for a second. But I'll tell you now, the net force is still 0, right? It still cancels because the force on top is 0, force on the bottom is 0, force on the right points out, force on the left points in. So the net force is 0, but what is the net torque? It's not 0, right? And how do I know it's not 0? Well, we can go ahead and calculate it, but I know it's not 0 because think about if I pull up on the right and I push down on the left, the loop is going to rotate about its center axis. So in order to figure out the torque, the easiest thing is going to be to draw a center axis. Whoops, I don't know what that page was. Is to draw a center axis and calculate the torque about that center axis. So let's go ahead and call this my axis of rotation and figure out the torque about that center axis. Let me see what this was. This was just a repeat. Many repeats. Okay, I guess I left off there when I was writing things down. So what's the torque, right? So now we've got to find the torque on this loop. Well, remember, in order to find the torque, right? Torque for any given force is, I got to make my pen smaller. The torque for any given force is R cross F, where R is the radius vector from the axis of rotation pointing towards the force, and F is the force. And therefore the net torque is going to be the sum of the individual torques. In this case, we have two torques. So we've got an R vector that points here, and we've got an R vector that points here. What is the length of each of these R vectors, right? So let's just go ahead and do the torque on the right. The torque on the right, the length of that R vector is just W over 2. Oops, let me give myself hold on a second. Rewritten it at the bottom here. The torque due to the force on the right is the radius vector to the force on the right from the axis of rotation crossed with the force on the right. That can be written as the magnitude of the radius vector times the magnitude of the force times the sine of the angle between them with a direction given by the right-hand rule. So I'm going to go ahead and now write that along the side, right? So that the torque on the right is the magnitude of the radius vector, which is W over 2, the width over 2, times the magnitude of the force, which is IHB, times the sine of the angle between them. And what's this angle between the force on the right and the radius on the right? 90 degrees. Sine of 90 is 1, so that just gives us 1. And so that's the magnitude of that torque. We'll talk about the direction in a second. What's the magnitude of the torque on the left? Well, the magnitude of the torque on the left is actually going to end up being the same thing. It's W over 2 IHB, and the angle between the radius vector and the left force is 90 degrees, so that's sine of 90 is 1. So the two torques are the same, but they're not in opposite directions, right? So think about the torque on the right. There's a couple of ways to think about the direction of the torque on the right. One is that it would tend to rotate the loop about that axis. So the loop rotates, kind of hard to say, out of the page on the right. That would rotate it, oh gosh, hold on. Okay, I tried to show it with the little black arrow in the center, right? That the loop on the right is going to come out of the page and it would tend to rotate around the axis and go into the page on the other side. The torque on the left is the same thing because the force is pushing in on the left. It's going to tend to rotate it, push the left into the page and pull the right out of the page. So those two torques are in the same direction. One way of talking about the direction is to look at what R cross F is, right? The direction given by the right-hand rule. So I'm going to redraw my R vector. My R vector is pointing out this way, and my F vector is coming out. By the right-hand rule, you take your fingers and you put them in the direction of the R, right, the first thing before the cross product, and you rotate them towards the F. F comes out. So you're putting your fingers in the direction of R and rotating your fingers out of the page. So your thumb points down the page. So that means that the net torque, the torque on the right, points down. And you find the same thing on the left, right? So if you take the R vector and you just draw it out here, and you go R cross F, you put your fingers in the direction of R, you rotate them towards F, which is into the page, so you rotate your fingers into the page. Your thumb points down, so the net torque on the left is down, so they're both in the same direction. And so a down means that the thing is going to rotate in the way that that little arrow in the center shows, around the axis that way. If we had looked from the top or the bottom, we could have said clockwise or counterclockwise. If we look, let's say, for example, put my eye, look at the top of the page. I'm putting my eye and facing down. This whole thing, if you're looking down on it, is rotating. It's rotating clockwise. If you're looking down on it. In any case, the two torques on the left and right are the same, so that means that the net torque is the sum of these two torques, and the thing is then going to rotate, and we'll just call it down. That means it's around the down axis. So the net torque, summary of what I just said, when you add those two torques up, you get this, and so the net torque is WIHB, whib. Down. You just count on the fact that you know that down means that the down means that it rotates around that axis. And it actually rotates around that axis in a sense of a different right-hand rule. If you put your thumb in the direction of that downward direction, your fingers show which way it rotates. Your fingers rotate in the direction that the object will rotate. So that's what it means to rotate down. WIHB is also equal to IWHB. And notice that W times H is area. It's the area of the loop times B. Or we would just write I, A, B down, understanding that A is area. Okay, so that's the net torque on the loop. There is a net torque on the loop, and a net torque on a loop of wire in a magnetic field will rotate. It's in this orientation given. But what happens when it rotates? We will come back to that another time. But here we've calculated the net torque. There we go, net torque on a current loop in a magnetic field in this orientation.